Richie here with day 2 of 14 concepts in a fortnight, 14 days, if you will. The idea here is to give you just 14 little snapshots, bite-sized pieces a day in the run-up to the May CFA Level 1 exam. Now, yesterday we hit shortfall risk, the safety first ratio and shortfall risk, which involved having a look at a normal distribution. So today we're going to still have a look at distributions. It's going to be a T distribution, but we're going to look at type 1 and type 2 errors and how we can interpret the distribution of the sample means. It's much more important, in my opinion, in hypothesis testing to understand the interpretation, to understand the output, the type 1 errors, the type 2 errors, than it is to sit there and stress about formula after formula after formula. So if you can understand type 1 and type 2 errors, you're well on your way. What I've done here is set up an example, and the golden rule in engaging people with this kind of material is to give them a realistic data set, a population that ignites their interest. So with that in mind, I've completely ignored it and gone for a population that consists of the numbers 1 through 5,001. Now, there is a method to that madness. The reason I've done it is because now you know what the population is, and you can very easily calculate the population mean as 2,501. So we have the answer to what we're about to try and find out. That's the idea. That's why it's there. So you know I've not made stuff up. I'm not just creating numbers to try and demonstrate something. I am actually proving something. So everything on the left here is knowledge you wouldn't have if you were actually trying to do the hypothesis tests we're about to run. But we just happen to know that the mean we're looking for is 2,501. What I've done is take a series of samples. You'll find if you were to actually swipe right, so to speak, you'd see I've done 50 samples. These samples are all of size 30. Excel did it for me. And for each of those samples, I've calculated the sample mean, sample standard deviation, and hence the standard error. You can easily run through the calculations just to get that. Quick note, I've calculated standard error as S over root N. I know, strictly speaking, we do know the population standard deviation here. So we could have used sigma over root N and a normal distribution and a Z, but that's not usually the way it works. As I say, this, we shouldn't really know when we're doing the test. This is just to show and understand what type 1 and type 2 errors are about. So we're going to assume we don't know. We're going to use S over root N, which is why we're using a T distribution. So we've taken a sample mean, taken a sample standard deviation, calculated the standard error as S over root N. N, as I say, is 30. Now, the hypothesis test we're going to do, we're going to test the null that the population mean is equal to 2,501, which of course we know it is. The alternative, it is not equal to 2,501. As I say, we know it is. So we know that that is correct. The null is true, but we're going to test it using all of our samples. To do that, because we calculated the standard error using S, the standard deviation of the sample, we are going to use a T distribution and hence a T-stat. To calculate the T-stat, we take our sample mean, so for our first one here, 208513, and we knock off our null. The numerator just tells you how far away in absolute terms are you from the null. But without taking into account the dispersion, we can't say whether that's far enough away to reject the null or not. So we divide it by standard error, 245.34. If you were looking at a population here and just doing a confidence interval, this would be a standard deviation. Here, we're using the distribution of sample means, every single possible sample mean. So we're using standard error instead. That's a measure of the imprecision or the precision of our estimates of this population mean from the sample mean. So I calculate my T, which turns out to be minus 1.695. That tells me it is 1.695 standard errors below the null. Is that far enough away to reject? We need a critical, which is going to be 2.045. You would need a table or you'd need to be given that T. It depends on the degrees of freedom. So with 30 observations, we'd have 29 degrees of freedom. And for 5% significance, which is what I'm using here for a two-tailed test, you get, in the tables you're given, 2.045. It's the interpretation that's key. Our calculated T, 1.695, in absolute terms, because it's a two-tailed test, in absolute terms, is less than the critical of 2.045, which means we fail to reject the null. Why? Well, here is our t-distribution. This is where we rely on the central limit theorem. The central limit theorem says for sample sizes that are large, even if your population is non-normal, this is non-normal, even if your population is non-normal, for large sample sizes, your distribution of sample means will be normally distributed with a mean equal to the population mean and a standard error equal to sigma over root n. Now, we didn't use sigma, we used s, which is why we're saying this is a t-distribution. But the point is, in this t-distribution, we've picked our critical t's here, so minus 2.045 plus 2.045, such that given the way our distribution is, our distribution of sample means, only 5%, it's symmetrical, so 2.5, 2.5, only 5% of all of our possible sample means will lie in those areas. In other words, this is the way to think about it. There is only a 5% chance that your sample mean would be in these rejection areas if the null was true. Now, given that we were not in those rejection areas, where were we? Calculated minus 1.695. So in here, given we are not in those regions, we do not have enough evidence to reject the null. We will fail to reject the null, which in this case, and this is the true genius of knowing what the distribution looks like, we know is the correct decision. Yay, we got it right. Now all we're going to do is repeat that 50 times. Now, clearly you don't want to see me do that, so I've just done the calculations. Here they are. Believe me, these are all correct. Obviously, the critical value is not changing, but here are all of our sample means. And for each sample mean, for each sample, the standard deviation, hence standard error, hence calculated t, critical, and the decision. And look, failing to reject. Every sample you can see on your screen, we are failing to reject. We are getting it right every time. And, gotta stress this, we only know we're getting it right because we happen to know the answer. But if we keep going, you'll see we do fail to reject with almost all of these samples, except finally here, this is a random sample of 30 taken from the population of 1 through 5001, but it gave us a calculated t of 2.703. The critical was 2.045. For this one, we were in the rejection area. We say there's only a 5% chance that if the null was true, we would end up in that area. So with a 5% significance, we reject the null. Now, again, we happen to know that that is the wrong decision. We have rejected the null when actually it was true. How can that be? Well, it's because we have these rejection areas. We are accepting the fact with a 5% significance that there is a 5% chance we'd end up in there. Look, I rejected. I said I'd done 50 samples. How many times did I end up rejecting? Well, one there. Look at this, back to back. One there, so that's 3. Then every other one was failed to reject. Just to prove it, look, that was 50 samples. So 3 out of my 50, I rejected the null. 3 times I got this decision wrong. 3 type 1 errors. Now, if I look at that, 3 out of 50, what's that? That's about, well, it's not about, is it? 3 out of 50 is 6% of my samples I ended up rejecting. We said using our critical value, it should be about 5. Well, that's pretty close, isn't it, for only 50 samples. The point of the exercise, we rejected a null even though we happen to know it was true. It's just a limitation of the test. The fact we need to use a significance level. These tails just keep going on. You can't get 100% accuracy. Now, if that's a type 1, you might be asking, what is a type 2? Well, a type 2 is opposite in every respect. If a type 1 is to reject, a type 2 has to be failing to reject the null. It's got to be opposite. If it's rejecting the null when true for type 1, type 2 has to be failing to reject the null when false. Now, I'm not going to go through all the calculations again, but you can set yourself up one of these very easily. Redo it now. Imagine if I tested a hypothesis asking whether the population mean was 2,700. We happen to know that it is not. The alternative would be that the mean is not equal to 2,700. We then started to take our samples. If I had one of these tests that ended up saying, oh, look, we failed to reject, that would be a type 2 error. So the focus here, the idea has been to focus on interpretation, not to sit down and plod through all of the formulas. Yes, you need to be able to calculate it. I think for a single mean, probably not for the rest of them. But it's to show you if you keep sampling, most of the time you'll get it right. For the type 1 error, because the probability of is the significance level, it's very easy to visualize and see it. Much more difficult to calculate the probability of a type 2 error. Not a calculation that's in the curriculum, so not something to worry about. But don't be sucked into saying probability of a type 1 is 5, probability of a type 2 is 95. That's nonsense. That would give you a 100% chance of an error, and the test would not be worth doing. So, more to come in the next, what have we got left? 12 days. But that is type 1 versus type 2. If I was you, I'd go into the exam knowing what they are, knowing what they represent, knowing how and why we get the probability of a type 1 error.